All right, good morning, everyone. So we got a couple more things to talk about in this chapter, and we'll be done with this chapter, and then we'll talk about some group assignments and things like that. That will be fantastic. So anyway, so last time we talked about the fact that the pointing vector represented the energy which was carried by the wave. Well, we also know that waves also carry momentum. So let's talk about the momentum actually inside of the electromagnetic wave as well, which turns out to also be told to us by the pointing vector. So the pointing vector is also related then to the energy as well as the momentum. So let's say I have a wave which is coming in, and then it's going to strike this particular boundary. So it's coming in with an initial amount of momentum. Let's call that V0. Now, one of two things can happen. Either the light could be absorbed, which means it's just going to hit and then basically stop, or it can be reflected, which means it's going to hit and then bounce away. So we're going to pretend that when it hits and bounces away, that it has a complete elastic collision, which means that the initial momentum is exactly equal to the final momentum, which means that the difference between these two scenarios is that simply in this case, the change in momentum will be equal to only the initial momentum. And then for this one, the change in momentum then will be equal to twice of the initial momentum. Right? Remember, if I have vectors going in opposite directions, when I subtract the two, that simply adds the two together. Now, the result of this is that if it's absorbed, my change in momentum is half the size of when it is reflected. Now, what we also know is that when I have a change in momentum, when something hits a wall and then bounces off, that applies a force to the wall. Okay? So let's talk about the force. So this also gives a force, which is what we call the radiated force, because this is force which is applied by the light. So anybody remember how momentum relates to force from 205? Has to do with time. Would. So we call the radiated force that is equal to, actually the change in momentum divided by the change in time. So this is the force. Now it turns out in electrostatic magnetism though, that the change in momentum is actually equal to the change in energy divided by the speed of light. So we're just going to take this as a given. I'm not going to derive that for you. But in this case, that means that this thing is going to be then equal to what? 1 over the speed of light times the change in energy divided by the change in time. Okay, so this is what we call the radiated force. Talk more about that in a second. Now, if I have light, though, it keeps constantly hitting this wall and bouncing off and hitting the wall again and hitting the wall again, what that means then is just like we talked about when we talked about kinetic theory. If something goes around on this side, hits the wall on this side, bounces off, and then comes on this side, hopefully I didn't break that. I did that in one class. Anyways, and then it hits on the other side, and then goes back and hits on this side, what that manifests itself then is as a pressure. Right? So let's talk about pressure. So this is what we call the radiative pressure. Actually did that in one class. I bumped into the wall and I broke the wall. I came away and everybody was like, what? My huge body print into the wall. So surprisingly, I didn't get in trouble for that. Actually, in that same class, I also broke the tiles because I exploded the garbage can and I got tiles shoved up in the wires inside the wall and I broke some pint glasses and I did a lot of damage in that class. But anyways, so pressure, radiated pressure. So we remember that pressure, or that radiated pressure, is equal to the force per unit area. So this is our radiated force divided by our area. Now from the previous slide, we know this is then going to be equal to 1 over C times 1 over A times the change in energy divided by the change in time. Now, let's look at this term here. What is this thing? So this is the change in energy per change in time, which means that has units of watts, divided by an area, which means this is a watt per area, which is the same thing as a watt per meter squared. But as we saw last time, the pointing vector also has units of watts per area, which is the same thing as a watts per meter squared, because that thing is an intensity. So at the end of the day, this thing is then simply equal to the intensity, which is the average of the pointing vector, divided by the speed of light. Now, in general, the way they're going to write this now is we're going to write this as P rad is then equal to A times the intensity divided by C, where A is equal to 1 when I have absorbing. And then A is equal to 2 when we have reflecting. Again, when I went through this argument, what I was looking at was only when it was being absorbed. But now we also talked about the fact is when it hits and it bounces off, I get twice the amount of momentum, which means I get twice the amount of force, which means I get twice the amount of pressure. So in general, I'm just going to write this as P rad is equal to A, where A again is equal to 1 for absorbing, or 2 when this thing is perfectly reflecting. So good. So this is whenever light hits the surface, it's going to cause a pressure on that surface, which means it's going to cause a force. That means right now you're all feeling a force from these lights. You're also feeling a force from your friends. Because again, we have a temperature, we're radiating away energy, which means we're giving off light, but that light happens to be in the infrared, which is why we can't actually see each other unless we have other exterior lights on. We see the reflection of those lights off of that. But you're being constantly bombarded with force or with this pressure from the lights, which is coming from all these different sources. So our first question we can ask then is this a significant amount of force that we feel based off of being collided with light all the time? So let's look at an example. So my example then says we have radiation from the sun that reaches the Earth's surface, transports energy at a rate of 1,000 watts per meter squared. From there, I want to estimate the pressure and the force exerted on me, or actually more particularly my hand, by the sun. So let's look at that. So let's draw our picture. Here's our example. So here's the Earth. And here I am standing on top of the Earth. And here's my hand. Good. So there's my hand. It's more like a catcher's mitt, but anyways, that's my hand. So we're told simultaneously that here's the sun. This is giving off monochromatic light, just for make it easier. And then we're told by the time it reaches my hand, there's an intensity which is equal to 1,000 watts per meter squared, which again we know is simply the same thing as the average of the pointing vector. Good. So what I want to know, first of all, is what is the pressure on my hand? So let's look at the pressure on my hand. So I know the radiated pressure then is going to be equal to A times the intensity divided by the speed of light. So here we have to decide if this is reflecting or absorbing. Most of the time I'm going to tell you if it's completely absorbing or if it's completely reflecting, which means that will determine the A value. In this case, I'm going to pretend that I am absorbing, not reflecting. In reality, I'm very reflecting. But let's pretend. So let's say in this case, A is simply equal to 1. I'm very white, but we're going to be so in this case, we can say our pressure then is going to be equal to what? 1,000 divided by the speed of light, which is 3 times 10 to the 8th, which means that this works out to be numbers about 3 times 10 to the minus 6th pascals. So this is the pressure which my hand feels. So again, if I'm just standing outside on a nice sunny day, my hand then feels a pressure from the light hitting my hand of 3 times 10 to the minus 6 pascals. What's the force then? So I want to know now, what's the radiated force? Well, we know radiated force then is going to be equal to the radiated pressure times the area. So I need to know what's the area of my hand. So let's estimate. So let's say my hand is, I don't know, 20 centimeters long and then 10 centimeters wide. Just for fun. So we can say my hand is a rectangle. Awesome. So in this case, this is going to be then equal to 3 times 10 to the minus 6 times then 0.2 times 0.1, which is going to be the same thing then as what? 6 times 10 to the minus 8 newtons. So this is going to be about the force on my hand by the light hitting my hand. Now, as far as my hand sitting here, is that a huge amount of force? No. The pure weight of my hand is about maybe 2 newtons, somewhere in that ballpark. So this is what? About 0.6 nanonewtons compared to the sheer weight of my hand, which is about 1 newton. So the point is, again, for something large like us, for most cases, this radiated pressure or this radiated force is going to be something very, very small that's basically insignificant. But this is important for other scenarios. So for example, if you're talking about gas clouds in space, there are stars everywhere, which means there's light moving all the time, which means that create a large amount of force onto these gas clouds. causing them to actually collapse on top of each other. As they collapse on top of each other, that creates stars, creates galaxies. This is actually early formation of these things by just simply using radiated pressure to push all of these things together to create overdensities, which then creates galaxies and stars and all that good stuff. This also has a huge impact on things like TNA. There's something which is called optical tweezing. So optical tweezing is you can actually pull DNA by shining lasers onto it, typically crossed using like tweezers, and then you can apply enough force to DNA to pull it all the way out, which is why we know the length of DNA. You can also move things around which are fundamental particles. So for example, I can shine lasers onto them, for example, what's called laser cooling. In this case, I can actually slow down molecules in this air to a few centimeters per second by simply shining lasers at them. So in this case, if they're moving, I shine the laser in the opposite direction. In this case, I can use that laser to slow it down by using this radiated force. Also, this radiated force can be something very large if I increase the intensity. For example, LASIK surgery. In that case, you're using lasers to actually cut into somebody's eye. In that case, you're using the radiated force, which you're using an extremely high intensity. So in that case, you're going to create a big amount of force onto the object. So, like I said, in typical most cases, this force that we're going to feel is going to be something that's very small. But again, in certain circumstances, either I can increase the intensity, or for fundamental particles, gas clouds, things like that, this will be a substantial amount of force, and I can actually use this to manipulate things around. But anyway, this is what we call radiated force. So, again, radiated force has to do with the fact that we have momentum, and our wave carries momentum, where that momentum is simply related to the energy, which is related to the pointing vector. So all this comes back to the pointing vector. So again, what does the pointing vector tell me? It tells me the direction at which the wave is moving. It tells me the amount of energy it carries per unit time deposited onto an area. And it also tells me about the force, as well as the pressure, as well as the momentum carried by this wave. So that one little piece of information tells me a lot of different things. So, everyone's okay? One more topic to talk about, and then we'll be done with this chapter. And then after that, we'll do some group assignments. And the last thing is what's known as polarization. So what's polarization? So it turns out that some waves are polarized and some waves are not polarized. So what is polarization? So polarization refers to the axis of oscillation of the electric field within light. So this axis of oscillation is also what's known as the plane of oscillation. So what does that mean? So what that means is if I have polarized light, what happens in this case is that the electric field will only oscillate along one particular axis. That's it. So if I can create a source where all the light is polarized, that means is all the polarized, or the light which is coming towards me, has only electric fields which are oscillating on a particular axis. So this axis is what we call the plane of oscillation, which is then also what's known as the polarization axis. So what does that mean? So that means if I had here was my spatial dimension, so this was x and y. In this case, let's say my electric field is oscillating along this particular axis here. So this would then be my plane of oscillation, also known as the polarization axis. All it means is all the light which is coming towards me, all the electric field then just keeps oscillating along this particular axis. It doesn't vary in different directions. So it turns out we actually do create polarization. We create polarization when it comes to things like cell phones, radio waves, TV signals, things like that. So here in the US, if I remember correctly, we actually use horizontally polarized, which means when radio signals come to you, it's actually polarized along the horizontal axis, where in the UK, they actually use vertical polarization. So that's why when you put up antennas, usually part of your antenna goes this way and the other one goes this way. So you're picking up all the polarization, which is along this axis, where in the UK, they're actually doing it in the vertical axis. But again, not all light is actually polarized. So you could actually have unpolarized light. Let's talk about unpolarized light. unpolarized light is light that has no particular oscillation axis. No oscillation axis. So what does that mean? So that means if I was looking at light which is coming towards me, so let's say again this is the x direction, the y direction, what's going to happen then is I'm going to have some of the light oscillating along this axis, some of the light's going to be oscillating along this axis, some of the light will be oscillating along this axis, some of the light will be oscillating along this axis, and etc. So basically, as the light is coming towards me, there's no preferred axis. I just have oscillation along basically every possible axis. That's what we call unpolarized light. So sources of unpolarized light, of course, are things like UV lights, the sun, things like this, all give off unpolarized light. So there's no particular complete axis for this thing to actually oscillate about. But it turns out that for anybody who has sunglasses, especially polarized sunglasses, you can actually take unpolarized light and turn it into polarized light. And this is done by what we call polarizers. We'll talk about polarizers. Polarizer. So polarizer is a material used to polarize both unpolarized and polarized lights. So what do I mean by that? So what I mean by that is if I took unpolarized light and I run it through a polarizer, I will then polarize it in a particular direction. But if I have polarized light, which is already polarized in one direction, I can use a polarizer to then polarize it in a different direction. So I can actually rotate the axis at which it is actually oscillating about by simply using a polarizer. So what's a polarizer? So this is actually where Polaroids came from. So Polaroids are originally actually polarizers, but typically it's a material that has molecules, where these molecules set up basically long chains. So these are my long chains of molecules, which are going to be set up in a particular direction. So these are molecules, they're actually chains of molecules. So what happens then is if I have light, which is coming in, let's say in this case I have light, which is coming in here, so this is my light. What happened is that these chains of molecules then absorb the light in the direction of the chain, which means in this case, if the chains are set up horizontally, it's going to then absorb all the light which is in the horizontal direction and then let anything that's perpendicular to that actually come through. So this is the way that the polarizer works. So the molecules then absorb this light in the direction of the chain. So they absorb the light in the direction of chain. But lets the perpendicular direction go through. Okay, so this is the way that a polarizer actually works. So again, the light's going to come in, it's going to strike the polarizer. Anything along this chain is going to be then absorbed by the molecules themselves, but then the perpendicular component is going to be allowed to actually pass through. Okay, so this is what actually polarizes this light. Now, these guys I can arrange any way I want to. I can either arrange them horizontally, I can arrange them vertically, I can arrange them diagonally, whatever it is that I want, or I can simply take it, rotate it, and then polarize anything in that particular case. Now, the effect that this has onto light is going to depend on the fact if it's being already polarized or if it is actually unpolarized. So let's talk about the difference. So let's say I start off initially with unpolarized light. So that unpolarized light, so again, here's my unpolarized light, where it's oscillating in all possible directions. That's going to be coming through and then hit my polarizer. So what happens in this case? Well, what happens in this case then is that no matter how it is I have this polarizer set up, automatically when the unpolarized light comes into it, exactly half of the intensity of the light is going to be absorbed by the polarizer. So So no matter what direction that the polarizer is set up, whether it's vertical or horizontal or diagonal, what'll happen then is we have to think about each one of these arrows as basically being the superposition of two vectors. So, for example, this piece here is the superposition between a vertical piece and a horizontal piece. Same thing as this one, same thing as this one, same thing as this one. So this is just a bunch of vectors which are either pointing in the vertical direction or in the horizontal direction. Now, when I send that into here, this thing, say, is horizontally polarized, what happened then is all the vertical pieces are going to be absorbed, which means only the horizontal pieces are going to be allowed to pass through, which will then cut down the number of field lines which actually pass through, but through this by exactly 1/2. So let's say that this thing is what we're going to call horizontally polarized. So in this case, what will happen then is the light which passes through will then only be oscillating in the horizontal direction. So what happens in this case then is that the initial intensity that this thing has gets reduced down to a final intensity, which is then equal to 1/2 of the initial intensity. So no matter what the direction of my oscillation, or sorry, my polarization is, the intensity that this wave initially comes in with then gets reduced down to a new intensity, where that intensity has been reduced automatically by 1/2. So anytime I have unpolarized light, I run it through a polarizer. It will then become polarized in the direction of the polarizer, but its intensity will have dropped by 50%. What happens if I have polarized light? So in this case, let's say that I start off with light which is being polarized along this particular axis here, where this is at some angle of theta relative to the horizontal. And I'm going to pass this guy through then a horizontally polarized polarizer. So what's going to happen is once this light passes through, by the time it comes over here, what will happen then is the light will then only be polarized along the horizontal direction. So what we want to know then is what? By how much has the intensity reduced? So let's say initially this is coming in with an initial intensity. Afterward, this thing comes out with a final intensity. My light is moving, say, in this direction, it comes out from here to here. So what I want to know then is what happens to the intensity. Well, remember that, again, go back to our pointing vector, we know the intensity then is simply equal to what? The average pointing vector, which is then equal to the RMS value of the electric field squared, then divided by C times mu naught. So, great. All this means then is what? So initially, if this was my initial intensity, then this is going to be my initial RMS value times then squared, then divided by C times mu naught. Now, what happens then? So let's draw a picture of what is happening at this point here. So let's say inside of my polarizer, again, my polarized light initially is this way. My final polarization is going to be in this direction. So let's think about our electric field. So here, this is going to be my RMS value initially. This portion here is going to be my final RMS value. And again, I know this angle here then is equal to theta. So initially what I'm doing is, I'm going to take this initial amplitude here, which again, I'm just going to call the RMS value here initially, and I'm going to decrease it to this amount based off of this angle here. But how much of the electric field has actually gone through? So how does this guy relate to this guy? Let's think about this as the hypotenuse. This is the adjacent side, so basically which trait term? Cosine, right? So what happens then is afterward, once the intensity actually goes through, this is now only going to depend on the cosine portion of this original wave, which means that what? My final RMS value of my electric field then is going to be equal to the original RMS value of the electric field times then cosine of the angle between the two. So this then tells me that what? My intensity then is going to be equal to my final RMS value,
squared divided by c times mu naught. So this is the same thing then as my initial RMS value squared times then cosine squared of the angle, all divided by c times mu naught. But going back to here, the initial value squared divided by c times mu naught is simply equal to the initial intensity. So this is going to be the same thing then as the initial intensity times cosine squared of the angle between the two. So finally, what I get then is that the final intensity is equal to the initial intensity times cosine squared of the angle between the initial polarized wave to the final polarized wave. This is what's known as Malices Law. Should I know how to spell Malice? Malices Law. So Malices Law simply says then that the intensity of the wave gets reduced from the original intensity by then cosine squared of the angle between the two polarizations. So this is what's called Malices Law. So again, here we have to be a little bit careful. If I have a wave which is coming in, which initially is unpolarized, and I run it through one polarizer, this then says that it's going to reduce the polarization by exactly a half, or at least the intensity by a half, and then align it in the direction in which it's polarized. Then if I send it through a following polarizer, it's then going to reduce the amount of intensity again, but this time by Malices Law. So what would happen in this case then? Let's say initially I have unpolarized light. So let's say again, here's my unpolarized light coming through. I'm going to run that through a polarizer, which initially is horizontally polarized. And then I'm going to run it through another polarizer, which is then vertically polarized. What happens? How much intensity do I have at these? Zero. Exactly. Good. So what's going to happen is by the time it runs through here, exactly. So now what's going to happen is when it's in this stage here, it's all going to be horizontally polarized, but I'm going to have half of the initial intensity. So this guy's coming in intensity I0. This one has an intensity equal to simply half of I0. But then by the time it comes through the final one, since this one is 90 degrees out of phase from which this one was originally oscillating, I have zero amount of oscillation. Which means that I have no light actually passes through, which means by the time it gets to here, we have zero amount of intensity. Now, what happens though, if I put in another polarizer here, which is polarized at a 45-degree angle? And in this case, I'm going to let anything which is along this axis here pass through. How much intensity am I going to get in this case then? Am I still going to get zero? No, I don't. Which is one interesting thing that actually happens with lights. So what happens with lights is, as long as I put in an intermediate polarizer, what will happen then is it goes from being polarized along the horizontal direction to now polarized along the 45-degree direction, which means by the time it comes back to the vertical direction, I now have a non-zero piece along the vertical direction, which means I've gone from zero intensity now down to a non-zero intensity. So you can again rotate the axis at which it is actually oscillating about by just simply using different polarizers. So again, by using these two, you get nothing, but putting in an intermediate one, you can actually get a non-zero intensity. Which is actually kind of interesting. Okay? So in this case, using a green one, this would no longer be zero, but it's going to be something kind of small. What's up?
It's still going to be less than.
It's still going to be less than the initial. That's right, because automatically I've already decreased it by half. And now from here, then I would have to now use the next one. So then I'd have a cosine of 45 squared, and then after that I'd have another cosine of 45 squared. But we'll do an example and see how this works. Okay? So light can do some kind of cool things. So let's use this and let's do an example. Yes. Good. So this says that we have initially unpolarized light is sent into a system of three polarizing sheets whose polarization directions make angles. Theta 1 equals theta 2 equals theta 3, which equals 50 degrees. So that means is that this angle here is 50 degrees, this angle here is 50 degrees, and then this angle here is also 50 degrees. All with the y-axis. So what then is the percent of the initial intensity is transmitted by the system? So basically what I want to know is by the time it comes down out of here, what then is the fraction of the amount of the initial intensity coming through that we have left over? So how much intensity is actually coming through? So by how much did this fraction decrease? Okay, so let's talk about this. Let's draw our picture. So we put in polarizer number 1 here, polarizer number 2 here, polarizer number 3 here. And here's my y-axis. So we're told initially this is theta 1. This one, so this is theta 2. This one, this is theta. There we go. And this is theta. But we know that theta 1 is equal to theta 2, which is equal to theta 3, which is equal to 50 degrees. Good. So initially, we have light coming in. So this is our initial intensity of the light, but again, this is unpolarized. And then at the end of the day, I'm going to have light coming through here, which I'm going to call I3, because I have I1 here. And this is going to pass through, which is going to become I1. That's going to pass through here, which is then going to become I2, and then finally make it to I3. So at the end of the day, what we want to know is, what is then the ratio of I3 to I0? So what is this? So how much, what's the fraction that passes through in terms of the energy? So good. So let's first concern ourselves with I1. So I1. So initially I have what? Unpolarized light, which comes through the polarizer. And as we said, what has to happen then to the intensity as it passes through the polarizer? Cut in half. So this is automatically going to be just simply equal to the initial intensity divided by 2. So now what's happening though is that our light though, on this intermediate part here, is now oscillating along the axis of theta 1. So this is the direction in which it is oscillating. So it's oscillating along theta 1. Good. So now let's think about I2. So for I2, well, I2 then is going to be equal to what? I1 times then cosine squared of the angle between the two. Right? So what's the angle between the two? So let's draw a picture. So what's happening here is that this one is oscillating here at theta 1. Theta 2 is down here, which means this entire angle here is theta. So theta is the angle of this wedge here, because this is the angle between this oscillation plane and the plane at which it now wants to oscillate. So this is my angle of theta. So how am I going to find theta? Well, I know since this is a horizontal line here, this angle here plus this angle here plus this angle here all have to add up to 180 degrees. So in this case, I then have to have that, well, theta 1 plus theta 2 plus theta must be equal to 180 degrees. Which means that theta in this case then is going to be equal to 180 degrees minus then theta 1 minus theta 2. We'll write all that down in a second. Now let's talk about I3. So I3 then is going to be what? I2, because that's the initial intensity which is coming through. Let's write that down. So it means I3 then is going to be equal to I2, because that's the intensity which is coming through, times then cosine squared of the angle between the two of those. But I'm not going to call it theta, I'm going to call it something else. What angle you want to call it? What's that? Phi? Phi. Sounds good. So what's phi in this case? Well, again, now what I know is that what, this thing is oscillating along theta 2, which means it's oscillating here, which means that what phi again is going to be this angle here. Right? So this is going to be phi, which again means that 180 degrees has to be equal to the sum of theta 2 plus phi plus theta 3. So that means phi then must be equal to 180 degrees minus then theta 2 minus then theta 3. Okay? Now, let's put all these things together. So what this means then is that what? I1 is equal to this. I'm going to insert I1 here. So this is going to become I0 divided by 2 times cosine squared of the angle. And then I2 is going to be all that. So I'm going to put all this into here to finally find I3. So let's put everything together. So it says that I3 then is going to be equal to I initial divided by 2 times then cosine squared of theta times cosine squared of
is then I3. Which means that I3 then is going to be equal to I0 divided by 2 times that cosine squared of 180 minus theta 1 minus theta 2 times cosine squared of 180 minus theta 2 minus theta 3. Now remember, I have cosine and I take 180 degrees minus an angle. That's the same thing as negative cosine of that angle. But since I'm squaring it, I don't care about the negative. That's just going to make the square or become positive. So it's going to be then I0 divided by 2 times then cosine squared of theta 1 plus theta 2 times then cosine squared of theta 1 or 2 plus theta 3. Okay with this? What?
Did you not just subtract the thetas because you already know what they are?
I could. I like algebra trade.
So you just got rid of the 180 because it's 1?
Well, because it's -1. That's right. Because if I had cosine of 180 minus theta, that's the same thing as negative cosine of theta. That's the same thing. But yeah, or I can just take 180 minus 100, which is an 80, and then gives me the same answer. Whichever way. I like algebra trade. I'm going to mute this. Okay, everyone's okay? So finally, what I want is the fraction. So I'm going to do is take this guy and divide by I0, because that's what we want at the end of the day. I'm going to get an I3 divided by I0, that is equal to 1/2 of all that stuff. Which then works out to be about 4.5 times 10 to the minus 4. So those means that the intensity finally divided by the initial intensity, that is 4.5 times 10 to the minus 4, which means that the final intensity is reduced from the initial intensity by 4.5 times 10 to the minus 4. Okay. And that's it. So these are polarizers. So again, polarizers are, again, whenever I have unpolarized light, it will automatically decrease the intensity by a factor of 1/2. And then once I send that light through a consecutive polarizer, and then we'll decrease the intensity by cosine of the angle between the two squared. If they're 90 degrees relative to each other, that means I get 0. So that's it. We're done with this chapter. So, having said that, we got some group assignments to talk about. Let's talk about the first one. The first one has to do with displacement current. So this says the magnitude of the electric field between two circular plates is time dependent. At t is equal to 0, the electric field is pointing upward, as shown in the diagram. The plates have an area of 0.04 meters squared. At any time larger than 0, what are the magnitude and direction, meaning upward or downward, of the displacement current between the plates? And then part C is the direction of the induced magnetic field clockwise or counterclockwise. Good. And then in this case, this is what my electric field looks like. So what that means is that the side of the electric field is decreasing over time because of that negative sign. So this is the electric field, just some constant minus another constant times time. So from this, you want to determine what is the magnitude of the displacement current, what is the direction at which it is pointing, and then from there is the electric or magnetic field clockwise or counterclockwise. So in this case, if you know that what the electric field or the induced electric field is downward because that's the direction of the displacement current, then your fingers will curl around in the direction of the magnetic field, which means we're going in this direction, which means that would be the clockwise direction by right-hand rule number 3. So this is the first one. We'll come back to that. From here, I got these two. The first one says we have a high energy pulse laser emits a 1 nanosecond long pulse of an average power of 1.8 times 10 to the 11th watts. The beam is 2.2 millimeters in radius. Determine A, the energy delivered in each pulse. So this is actually a nice easy question. Remember, power is energy per unit time, which means all you have to do is take that power and multiply by the time, which is 1 nanosecond. That's the amount of energy. Nice and easy. Part B then says, what is the RMS value of the electric field? So in this case, you're using the intensity, which is the average pointing vector, which in this case, we're just looking for the RMS value of the electric field. So that's what we just wrote down a little bit ago. That's E RMS squared divided by C E naught. Using the intensity, which in this case, the intensity is the power divided by the area. And it's a circular area. So that's a nice, easy question. Second one then is a force problem. So this is a radiated force. So this says during 2004, Japanese scientists successfully tested a solar sail. One of them had a somewhat complicated geometry that's modeled as a disk, which has a diameter of 9 meters, a thickness of 7.5 micrometers. And then the sail was located at a particular location where the intensity from the sun was 1,400 watts per meter squared. So in this case, you want to know what force did the sun's light exert on the sail, assuming that it struck perpendicular to the sail and that the sail was perfectly reflected, just to increase the amount of force as much as possible. So here you're just calculating the radiated force. Next part then, you want to know if the sail was made out of magnesium, meaning that it has a density of 1.7 grams per centimeter cubed, which is 1,700 kilograms per meter cubed. Remember, they're different by 1,000. What acceleration would the sun's radiation give the sail? So how fast would this guy actually accelerate? Part C, does this acceleration seem large enough to be feasible for space flights? So meaning, could you go large distances based off of this acceleration? The answer to that is no. I'll let you find that out yourself. And then explain why not. And then finally, in part D, in what ways could the sail be modified to increase the amount of acceleration? Now, the biggest thing I can get out of this one is, remember, for a fixed amount of force, because the intensity is fixed in this case, so it has a fixed amount of force, what do you have to do to the mass to increase the acceleration? You got to decrease it, right? F equals ma. So to get A to be as big as possible, m has to be as small as possible. So what you want to do then is think about how you can modify the structure of this thing to decrease the mass as much as possible to get this thing to accelerate the greatest. Great, and then we got one more. And the last one is actually just a polarization one. So similar to what we just did. So this is actually just two polarizers. So we have unpolarized light initially, which has an intensity of 45 watts per meter squared, is sent into the two polarizing sheets with directions. So this one is 70 degrees, this one is 90 degrees to the y-axis. So what is the intensity of the transferred light? So again, here, you know automatically when it comes through here, it's at half of this amount of value, which means it's now polarizing along this direction. So now your polarization is here. So you want this angle between the two of these. And then just take that half and then multiply by cosine of the square of that angle. And then you're done. So nice, easy questions. So not too bad. So that's 4 group assignments. Counting towards the final. 1. Okay. I'll bring this one back up. Did everybody sign that sheet of paper? No, sorry. Stop. You stopped. No. That's okay. I'll get it. So the sheet of paper, we're going to throw extra credit points at you for actually showing up. I don't know how many you have on it. What's up?
Just a fun question about solar cell. Did you know about the solar cell like back that circled around the top?
No, I didn't hear it.
I don't remember the name. It was like Mahamalama or something. Right? It was something long, just weird name.
Gotcha.
It was like an asteroid or something like that. They had like just like aliens or something.
Oh, gotcha.
Like you around the sun, like a weird kind of like solar cell.
Oh yeah, I did hear about that. Okay. Yeah, I didn't hear too much about it.
Because I was like in the astronomy class in high school or whatever, and then my teacher brought it up.
Yeah.
It's pretty cool.
I didn't hear about the mysterious thing they saw floating around the sun. I didn't hear about that. That's about as much as I heard about it. I'll have to take a look. Everybody sign the sheet? Yes. Good. about the thing going around the sun, but I didn't. Kind of disappeared after.
Yeah, that's what my neighbor told me. I was like, is it possible it could be like a solar cell or something like that? That'd be cool. It's just like,
The aliens just hanging out for some reason.
why would they just not say this?
They're probably scared of us. What's up? Yeah.
So.
Yep.
But then we also.
Correct. So when we talk about the polarization, we're always talking about the aspect of the electric. So not about the magnetic. So we know the magnetic is automatically 90 degrees of that, and it's determined by the rating rule what direction it's off.
So polarized.
Well, they will affect the magnetic. Another way to the overall intensity. Because if I decrease the electric field, I also increase the magnetic. Remember, the electric field and magnetic field are always related to each other by the speed of light.
Okay.
So the answer to that is yes, it does affect the magnetic field, but
Indirectly, not directly.
correct. Correct. So what it really does is it typically, well, let's see.
So is anything polarized, is anything, would any kind of polarization affect the magnetic field? I guess.
Well, I guess it does the two simultaneously, even though we just talked about the electric. Because what the molecules are doing is they're overall absorbing. So to absorb light, it's simultaneously absorbing both electric and magnetic. They're not just doing it from one and then the other one is doing, I don't know, doing the same thing.
We're still defining the polarization in the direction of
The electric field.
Yeah, but you guys.
It's just the way we go.
I must have missed that somewhere.
Yeah. Probably when I was talking too fast. Yeah, so it's only defined in terms of the electric. Because we know the magnetic field is determined from the direction of both propagation. That's like whatever you think. Okay, so if my light is moving in this direction, I have to remember we said point of vector pointing in the direction of the propagation. So I mean, if it's moving that way, my thumb is in the direction. So it means if it's vertically oscillating, I mean, like I could feel that has to be this way. Horizontally, vertically, all based on.
Okay.
So as long as we know one of them in the direction it's moving, then we know. So that's why we don't typically talk about both of them, because one is determined from the other.
Actually following along.
There you go. There you go. So, yeah. So, I mean, we provide it for great. Have a good Thanksgiving. You too. Have a good weekend, everybody. Stay safe.
It's only Monday and you're saying have a good
I
weekend.
know.
This is wonderful.
So, then you're talking about.
Bye.
So how is that pulling together? Wow.
Oh, so imagine that, you know, if I have light on one side and light on the other side. So
Oh,
those have to
it's
be-
like by surrounding stars and putting it together.
Exactly. But otherwise, yeah, if I only have one star in existence and I had glass on, all you do is just push the glass off. But yeah, but we also have other hot things which have lights, you know, so for example, if I'm creating a galaxy or if I'm creating another star, I'm gonna have a lot of bright light. And all that light kind of coming from different directions will help collapse it down to it. Gotcha. Yeah. Nice.
Have a good one.
You too. Stay safe, Tim.